Hello there, and welcome to Science for Sleep. Tonight, we begin a quiet and unhurried journey into one of the most fundamental, most personal, and most misunderstood forces in all of existence. We are going to explore the nature of a presence that is with us every moment of our lives, yet one we can neither see, nor touch, nor hold. We are going to explore the nature of time. It is the invisible river that carries us all forward, from a past we can only remember, to a future we can only imagine. It slips through our fingers, it shapes our memories, and it occasionally plays the strangest and most wonderful tricks on our minds, especially when we are waiting for a kettle to boil on a cold morning, or for sleep to finally arrive in the stillness of the night. Before we begin to unravel this ticking, stretching, and sometimes vanishing tapestry of time, I would love to know, where in the world are you listening from? And what time is it for you right now in your corner of the world? It is a fitting way to begin our exploration, is it not? A journey into the nature of time, and here we all are, scattered across the globe, across dozens of different time zones, yet all arriving at this single quiet moment together, in our own unique slice of the clock. If you find this voyage soothing or intriguing, or simply a nice way to let the sharp edges of a long day soften and blur, I would be ever so grateful if you gave this video a like, and perhaps subscribe to this channel. It truly helps this little corner of calm reach others who might also be in need of a peaceful pause in their busy lives. Now, my deepest hope is that this journey is not so fascinating that it keeps you awake. But if it does, well, at least you will have learned something new about the very fabric of the reality we inhabit, before you finally drift off. So I invite you now to settle in, get comfortable, allow your thoughts to slow down to match the gentle pace of our exploration, and let us begin. Because somewhere between the seconds and the centuries, between our waking dreams and the deep of the night, lies the quiet and deeply strange story of time. Time has a funny and peculiar way of stretching and shrinking, doesn't it? An hour spent in a tedious meeting can feel like it contains several geological epochs, while an hour spent with someone you love or lost in a favorite piece of music can vanish in what feels like a fleeting, weightless instant. And yet the clocks on our walls, the atomic vibrations that govern our technology, all march forward with a steady, relentless, and seemingly objective rhythm, second after second after second. So what is going on? How can time feel so personal and flexible, and yet be, we are told, so absolute and rigid? The beginning of the answer to this profound question lies not in the distant clockwork motions of the stars, but much closer to home. It begins in the silent, intricate, and deeply mysterious universe that exists inside your own head. Our perception of time, that deep internal sense of duration of when things start and when they end, is a surprisingly fluid and malleable thing. Psychologists and neuroscientists call it subjective time, and it is a reality that is constantly being sculpted, stretched, and compressed by the forces of our own minds, by our attention, by our emotions, and by the very way our brain chooses to write the story of our lives in the form of memory. In other words, the way you feel about time at any given moment can be very different from the way time is actually physically passing. Let us start with the strange, elastic, and deeply familiar oddity of waiting. Imagine yourself in a quiet room with nothing to do. The walls are a pale, featureless beige. The magazines on the table are ancient, their pages worn smooth by the hands of countless other waiters. The only sound is the slow, deliberate, almost judgmental tick-tock of a clock on the wall. 5 minutes in that room can feel like half an hour. That is because your brain, when it is starved of new and interesting information, when it has no external stimulation to focus on, turns its vast attention inward, and that intense internal focus on your own thoughts and feelings makes you acutely, almost painfully aware of each passing second. You begin to notice the space between the ticks of the clock. You begin to feel the duration of every breath, and time, under this intense and unwelcome scrutiny, seems to slow to a thick, heavy, and sluggish crawl. Now let us contrast that with a completely different experience. Imagine yourself in a lively, joyful conversation with a dear friend. so engrossed that the rest of the world seems to fade away. Or imagine the experience of being completely lost in a creative act, painting, writing, playing an instrument. In those moments you are fully engaged, your attention is directed outwards, your brain busy processing a rich and constant and meaningful stream of information. And because it is so busy, it is not keeping a close watch on the clock. It is as if your mind's internal timekeeper says, we are occupied with something wonderful. There is no need to count the seconds. I will just let this unfold. And so time seems to dissolve. It loses its weight, its texture, its very presence. And before you know it, hours and hours have flown by in what feels like mere minutes. This is a state that psychologists have famously called flow, a state of deep and effortless immersion, where our sense of self and our sense of time can seem to fade away, leaving only the pure, joyful experience of the present moment. The novelty of an experience also plays a powerful and crucial role in how we remember the passage of time. When you encounter something new or unfamiliar, your first day at a new job, a trip to a city you have never visited before, your brain has to work harder. It cannot rely on old routines or mental shortcuts. It has to take in extra information to process all the new sights and sounds and smells, and it stores these experiences as dense, rich and detailed memories. Later, when you look back on that period, your brain accesses this wealth of detailed mental footage, and it concludes that more time must have passed, because so much happened. This is why our childhood summers can seem in our memory to stretch on for a beautiful eternity. For a child, the world is a constant, unending stream of new experiences. The brain is constantly learning, constantly exploring, constantly logging new information, and creating a dense and detailed archive of memories. As we get older, our lives often fall into predictable and comfortable routines. We drive the same route to work. We eat the same kinds of food. We see the same people. There are fewer truly new experiences, and our brains, which are incredibly efficient, get very good at compressing these routine memories. An entire uneventful week at the office might be stored as a single simple memory marker, another week at work. And so when we look back at the end of a year, there are fewer distinct highlights, a much shorter reel of memories. And time in our recollection seems to have sped up, to be slipping away faster and faster with each passing year. Our emotions too are powerful sculptors of time. Scientific studies have shown that intense emotions, particularly fear and anxiety, can dramatically slow down our perception of a moment. There is a theory that during a sudden dangerous situation, a car accident, a sudden fall, our brain's amygdala, the center of our fear response, kicks into an overdrive mode of memory formation. It begins to record far more details per second than it normally would, capturing every fragment of the experience in high definition. Later, when we are safe and we play back that memory, it is so dense with information that it feels as if it happened in slow motion. It is not that time itself actually slowed down. It is that our brain's camera switched from taking simple snapshots to recording in ultra-high definition video, creating the powerful and persistent illusion of a stretched-out moment. So, what is time? At least as we humans experience it. It is not a single objective thing. It is not just a number on a clock or the shadow of a sundial moving across a stone. It is a feeling, a perception. It is a beautiful and sometimes frustrating magic trick played by our memories and our attention. It is a deeply personal and wonderfully flexible reality. It changes with our mood, with our age, with our culture, and even with the language we speak. It speeds up when we are in love, it slows down when we are afraid, and sometimes when we are truly deeply present in a moment of joy or concentration, it seems to vanish altogether. And while physics may eventually explain to us what time is on the grandest, most cosmic of scales, our personal sense of time, our journey through our own subjective river of moments, will always be something that is deeply, wonderfully, and at times delightfully and maddeningly unreliable. It is a clock that is built not of gears and springs but of thought and of feeling. For the vast majority of human history, time was not a number on a screen. It was a story told by the world itself, Our most ancient ancestors did not measure time in the way we do now. They lived within its great repeating and sacred rhythms. Their first and greatest clocks were the celestial bodies themselves, the grand, silent, and perfectly predictable engines of the cosmos, turning in their slow and majestic dance across the sky. The most fundamental of all rhythms was the simple and profound cycle of light and darkness. The rising of the sun was the beginning of the day, a time for hunting, for gathering, for work. The setting of the sun was the coming of the night, a time for rest, for stories, and for huddling close to the deep, primal warmth of the fire. This was the first and most powerful division of time, a simple binary of day and night, of activity and of stillness, a rhythm woven into the very fabric of our biology. As societies grew more complex, so too did their need to divide the day itself into smaller, more manageable pieces. The first true timekeeping devices were born from a simple, elegant observation, the movement of a shadow. In ancient Egypt, as far back as 3,500 years ago, great, towering stone obelisks were erected in the courtyards of temples. These were more than just magnificent monuments to the gods. They were colossal sundials. As the sun god Ran made his daily journey across the heavens, the long, sharp shadow of the obelisk would creep across the marked ground below, a silent, divine finger pointing to the passing of the hours. The Egyptians and other ancient cultures, like the Babylonians and the Romans, developed smaller, more portable shadow clocks, but the principle remained the same. Time was a function of light, a gift from the sun. This early sun-based time, however, was not the rigid, uniform time we know today. The hours of the ancient world were not of a fixed and equal length. The period of daylight was simply divided into 12 equal segments, regardless of the season. This meant that an hour in the long, sun-drenched days of summer was much longer than an hour in the short, fleeting, precious days of winter. It was a flexible, organic, seasonal time, a time that stretched and shrank with the very breathing of the earth itself. But this complete reliance on the sun had its obvious and frustrating limitations. A sundial is useless on a cloudy, overcast day, and it is completely, utterly silent during the long, dark hours of the night. Humanity needed a new kind of clock, one that could operate independently of the heavens, a timekeeper that could be brought indoors, into the monastery, into the home. And so, our ancestors turned to another of the great classical elements, water. The water clock, or clepsydra as it was known to the Greeks, was a true and profound revolution in timekeeping. In its simplest form, it was a large stone vessel with a small, carefully calibrated hole near the bottom, which would allow water to drip out at a slow and relatively steady rate. Lines marked on the inside of the bowl would indicate the passing of the hours as the water level silently dropped. These were the first clocks that could measure time in the dark, the first to free humanity from its complete dependence on the sun. Later, the brilliant engineers of the Hellenistic and Chinese worlds would create far more complex and ingenious water clocks, with intricate systems of gears, floats, and siphons, which would trigger automata, small mechanical figures of people or animals to strike bells or move their arms to mark the passing hour. It was the beginning of the idea of time as a machine, a human-made device that could imitate the steady flow of the cosmos. And yet, for all their ingenuity, these early clocks were still tied to the natural world. Their flow was imperfect, their accuracy dependent on the changing temperature and pressure of the water. The next great leap in the story of time would come from a desire to detach time completely from the rhythms of nature and to transform it into something purely abstract, purely mathematical, and perfectly, relentlessly regular. This was a revolution that began in the quiet, contemplative, and highly regulated world of the medieval monasteries of Europe. The monks of the early Middle Ages needed to regulate their day with a new and profound kind of precision. Their lives were structured around a strict schedule of 7 daily prayers, the liturgy of the hours, and they needed to be woken reliably for vigils in the middle of the night. For this, a sundial or a simple water clock was simply not enough. And so, in the high, cold towers of their abbeys and cathedrals, the first great mechanical clocks were born. These were not the small, delicate clocks we know today. They were colossal, room-sized machines, intricate and powerful tangles of iron gears, heavy ropes, and immense falling stone weights, and at their very heart was a new revolutionary and world-changing invention, the verge escapement. This was a clever mechanism, a small toothed wheel and a pivoting rod with two small pallets that would catch and then release the energy of the falling weights in a series of small regular and precisely controlled steps, and with each release the clock would make a sound, a sharp, distinct and strangely new sound, a sound that had never been heard before in human history. Tick-tock, tick-tock. This sound, which echoed out from the church towers across the towns and cities of late medieval Europe, was the sound of a new world being born. It was the sound of time being tamed. For the first time, time was no longer a silent, continuous flow like water or a shadow. It was a series of discrete, identical, and quantifiable units. It was a rhythm that was not natural but purely mechanical, and this new mechanical time began to change everything. The workday, which had once been defined by the rising and setting of the sun, could now be divided into equal paid hours. Appointments could be made with a new and binding precision, and society itself began to synchronize to the steady, impartial, and relentless beat of the clock. This quest for ever greater precision became an obsession that would drive centuries of innovation. In the 17th century, the brilliant Dutch scientist Christian Huygens, inspired by the regular isochronous swing of a pendulum, created the pendulum clock. It was a breakthrough that increased the accuracy of timekeeping from a matter of minutes per day to a matter of mere seconds, and in the 18th century, the great unsolved problem of navigation at sea, the problem of determining a ship's longitude, was finally solved by an English carpenter and self-taught clockmaker named John Harrison. After decades of obsessive single-minded work, he built a marine chronometer, a clock so robust and so precise it could keep near-perfect time on the violent rolling deck of a ship at sea, allowing sailors for the first time to know their exact position on the globe. With these incredible inventions, humanity had seemingly achieved its ancient goal. It had created a time that was external, that was objective, and that was, for all intents and purposes, universal. And this new mechanical and perfectly predictable time provided the perfect philosophical foundation for the scientific vision of the universe's greatest architect, Sir Isaac Newton. In his great work, the Principia Mathematica, Newton laid out his laws of motion and universal gravitation, the laws that would govern science for the next 200 years. And to do so, he needed a concept of time that was just as steady, just as reliable, and just as predictable as the clocks that were now ticking in the great observatories of Europe. And so he formalized the idea of absolute time. Let us linger on this powerful and deeply beautiful idea. For Newton, time was not a product of the world. It was the backdrop for the world. He imagined time as a single great invisible river flowing at a constant and unchanging speed everywhere in the universe and for all of eternity. This river of time was absolute. It did not speed up for one person and slow down for another. It was not affected by motion, by gravity, or by anything else in the cosmos. It was the universal divine clockwork, the steady, impartial metronome against which every event in the history of the universe could be measured. This vision of a clockwork universe governed by predictable laws and unfolding against a backdrop of absolute time was a profoundly comforting and powerful one. It brought a sense of order and reason to a universe that had often seemed chaotic and mysterious, and for over 200 years it was the undisputed foundation of all of science. As you drift now deeper into the quiet of the night, imagine this great silent river of absolute time. See it flowing steadily and serenely from the very beginning of all things towards the very end. It is a beautiful, orderly, and deeply peaceful vision of the cosmos. Humanity, in its long and patient search for a time it could trust, had finally found one. For 2 centuries we lived comfortably within this clockwork universe of Isaac Newton. Time was a single great river flowing at the same speed for everyone. It was a simple, elegant, and powerful idea. And for everything on Earth, from a falling apple to a rising tide, it seemed to be true. But as our science began to probe the universe at its extremes, at speeds approaching the very limit of light itself, we began to notice that the great universal clock had a problem. It did not tick the same for everyone. The single great river of time, it turned out, was not a river at all. It was a fabric, one that could be stretched and squeezed and warped. The age of absolute time was about to end. The age of Einstein and of relativity was about to begin. Our story now takes us to the early years of the 20th century, to the quiet, cobbled streets of Bern, Switzerland, and to a young, unassuming patent clerk, a man with a rebellious spirit, a deep and playful curiosity, and famously unruly hair. His name was Albert Einstein. During the day he would examine technical drawings for new inventions, but in his spare moments in his mind he was conducting some of the most profound and revolutionary thought experiments in the history of science. He was not just thinking about the universe, he was reimagining its very foundations, and his first target was Newton's great absolute river of time. Einstein began with a simple but deeply paradoxical observation about the nature of light. Experiments in the late 19th century had shown something incredibly strange. The speed of light in a vacuum is always the same, for everyone, no matter how fast they are moving. This seems at first to be a complete violation of common sense. Imagine you are in a car driving at 50 miles per hour. If you throw a ball forward, someone standing on the side of the road would see the ball moving at its thrown speed, plus the 50 miles per hour of the car. But light does not behave this way. If you are in that same car and you turn on your headlights, the light from those headlights does not travel at the speed of light plus 50 miles per hour. It travels at the speed of light, and if a spaceship were to fly past you at half the speed of light and turn on its headlights, the light from that spaceship would still travel at the exact same speed of light. This is the unbreakable universal speed limit. It is the one fixed and absolute constant in the entire cosmos. And Einstein realized that if the speed of light is the one thing that never changes, then something else, something we thought was absolute, must be flexible, and that something is time. This was the heart of his special theory of relativity. Published in his miracle year of 1905, he showed that time is not a separate, independent entity. It is deeply and inextricably woven together with space into a single four-dimensional fabric that he called space-time. And the faster you move through the dimensions of space, the slower you must move through the dimension of time. To understand this, let us use a famous thought experiment. Imagine a clock that measures time by bouncing a single photon of light between two perfectly parallel mirrors. Tick, the photon leaves the bottom mirror. Tock, it hits the top mirror and is reflected back. Now imagine this light clock is stationary, sitting on a table in front of you. The photon of light is just traveling a short, straight path up and down. But now, imagine that same clock is on a spaceship, flying past you at an incredible speed. From your perspective, standing on the ground, the clock is moving. And so the photon of light inside it is no longer traveling a short straight path up and down. To get from the bottom mirror to the moving top mirror, it has to travel a longer diagonal path, and then another longer diagonal path, to get back to the bottom mirror. Here is the crucial point. We know from that one unbreakable law that the speed of that photon of light cannot change. It is always the same. So if the photon has to travel a longer distance but its speed is fixed, then it must take a longer amount of time to complete its journey. The tick-tocks of the moving clock from your perspective are happening more slowly than the tick-tocks of the clock sitting on your table. Time itself on that fast-moving spaceship has slowed down. This is the phenomenon of time dilation. This is not a trick. It is not a psychological illusion. It is a real physical property of the universe. The faster you move through space, the slower you move through time. This effect has been measured and confirmed countless times. The atomic clocks on fast-moving airplanes and GPS satellites really do tick more slowly than clocks on the ground. Particles called muons, which are created in the upper atmosphere and have a very short lifespan, are able to survive the journey down to the Earth's surface only because their incredible speed slows their internal clocks down, extending their lives from our frame of reference. This leads to the famous and deeply poignant twin paradox. Imagine two identical twins. One stays on Earth, while the other boards a spaceship and travels to a distant star at near the speed of light, and then returns. When the traveling twin steps out of her spaceship, she will be physically, biologically younger than the twin who stayed behind. For her, only a few years may have passed, but for the twin on Earth, decades or even centuries may have gone by. She has not just traveled through space, she has traveled into Earth's future. But Einstein was not finished. For 10 more years he wrestled with an even deeper problem: how to incorporate gravity into this new flexible vision of space-time, and in 1915 he published his masterpiece, The General Theory of Relativity, and it revealed that it is not just speed that can warp time, it is gravity itself. General relativity describes gravity not as a force that pulls but as a curvature in the very fabric of space-time, a curvature caused by the presence of mass and energy. Let us return to our analogy of a vast, stretchy trampoline. A massive object, like the sun, is like a heavy bowling ball placed on the trampoline. It creates a deep, curved dimple in the fabric, and a smaller object, like the Earth, is like a marble rolling around that curve. That is what an orbit is. Now imagine that the dimension of time is also part of this fabric, where the fabric is stretched most deeply by gravity. Time itself is stretched out. Time literally runs more slowly in a stronger gravitational field. The deeper you are in a gravity, well, the slower your clock ticks relative to a clock that is further away. This is gravitational time dilation, and like the effects of speed, it is a real and measurable phenomenon. The atomic clocks on GPS satellites, which are orbiting high above the Earth in a weaker gravitational field, actually tick slightly faster than clocks on the surface. If our GPS systems did not constantly correct for this relativistic effect, their calculations would be off by several miles every single day. Our modern daily lives literally depend on our understanding that Newton's absolute universal time is not real. To see this effect at its most extreme, we must travel to the edge of a black hole. Here gravity is so immense that space-time is warped into an almost infinite curve. If you were to watch a friend fall into a black hole, you would see a very strange thing. As they approach the event horizon, the point of no return, their time from your perspective would seem to slow down and down and down. You would see them move in ever slower motion, their image getting redder and dimmer until they seem to freeze forever at the edge. But for your friend, time would be passing normally. They would cross the event horizon in a finite amount of time and continue their journey to the singularity at the center, where time as we know it finally ends, finally ends, finally ends, finally ends. So what does this all mean? It means that the single great universal river of time that Newton envisioned does not exist. There is no master clock for the universe. Time is personal. It is local. It is relative. Every observer, every planet, every galaxy carries its own clock, and the rate at which that clock ticks depends entirely on its motion through space and its position in a gravitational field. The story of time is not a single linear narrative. It is a vast, interconnected and beautifully complex tapestry of different temporalities, all woven together into the flexible, dynamic fabric of space-time. As you drift now deeper into the quiet of the night, let go of the idea of a single universal now. Imagine the universe as a great, dark and gentle sea with countless different currents of time, all flowing at their own pace. Some are fast, some are slow, and you in this moment are simply floating in one of those currents on your own unique journey through space-time. The age of absolute time is over. The age of relativity has begun, and the universe has become a much stranger and much more wonderful place. Einstein's revolution taught us that time is not absolute, but its pace can change. but his equations, like Newton's before them, held a strange and deep symmetry. They worked just as well backwards as they did forwards. They describe a world where a broken glass could just as easily reassemble itself. Yet, in our world, glasses only shatter, eggs only scramble, and we only ever remember the past, never the future. The laws of physics seem to have no preference for a direction in time, but the universe clearly does. To understand this profound paradox, we must now leave the world of relativity and journey into the realm of thermodynamics, to ask the great question of why time has an arrow. Let us begin with a simple, quiet thought experiment. Imagine watching a video of a drop of blue ink falling into a clear glass of water. You watch as the small, perfect sphere of ink gracefully descends, and then upon contact with the water, it begins to bloom. It unfurls in beautiful, intricate, swirling tendrils of blue, slowly and chaotically spreading throughout the glass until the entire body of water is a uniform, pale blue. It is a beautiful, natural, and entirely familiar process. Now imagine watching that same video in reverse. You see a glass of pale blue water, and from its uniform color, strange, ghostly tendrils of a deeper blue begin to coalesce. They swirl and dance, pulling themselves together, contracting until they have gathered all the color from the water into a single perfect suspended drop of ink, which then leaps gracefully out of the water and back into the dropper above. This reverse video would feel strange. It would feel impossible. It would feel like magic. And yet, if you were to look at the microscopic interactions of the individual water molecules and ink molecules, the laws of physics that govern their collisions would work perfectly well in either direction, forwards or backwards. So why is it that in our universe the ink only ever spreads? Why do eggs only ever break? Why do buildings only ever crumble to dust, and dust never spontaneously assembles itself into a building? Why does time in our macroscopic world seem to have a preferred direction, a one-way street leading only from the past to the future? This is the mystery of the arrow of time. It is a term coined by the great British astrophysicist Sir Arthur Eddington to describe the profound and profoundly obvious asymmetry of time in our everyday lives, and the best physical explanation we have for this one-way flow is not found in the laws of motion or gravity, but in one of the most powerful and most misunderstood laws in all of science, the second law of thermodynamics. At its heart, the second law is a simple statement about probability. It says that in a closed system like our universe, the overall level of disorder, or randomness, will always tend to increase over time. The scientific name for this disorder is entropy. And the second law simply states that the total entropy of the universe is always increasing. Things, left to their own devices, will always move from a state of order to a state of disorder. To understand this, let us use a gentle and powerful analogy. Imagine you are on a beach, and you have spent a long and patient hour building a magnificent, intricate sandcastle. It has towers and walls and a moat. It is a highly ordered, complex and specific structure. There is only one way for all those billions of grains of sand to be arranged to form your perfect sandcastle. This is a state of very low entropy. It is a state of improbable order. Now imagine a gentle gust of wind or a single soft wave from the sea. The castle begins to crumble. The towers fall, the walls collapse, and soon all that is left is a random, messy, and unremarkable heap of sand. This is a state of very high entropy, a state of disorder. And here is the crucial point. There are trillions upon trillions of ways for those grains of sand to be arranged into a random heap, but there was only one way for them to be arranged into your specific sand castle. The universe does not have a will or a desire for things to be messy. It simply and always moves in the direction of the most probable outcome. And there are always vastly more ways for things to be disordered than there are for them to be ordered. The universe is just playing the odds. A sandcastle will always eventually become a heap of sand. A scrambled egg will never on its own become an unscrambled egg. A drop of ink will always spread through the water. And this, in its beautiful simplicity, is the arrow of time. The reason we experience time as flowing in one direction is because we are living in a universe that is on a one-way journey from a state of low entropy to a state of high entropy. The past is, by definition, the time when things were more ordered. The future is the time when things will be more disordered. The flow of time is nothing more and nothing less than the universe's slow, steady, and majestic slide into its most probable, most disordered state. This thermodynamic arrow of time is the master arrow from which all the other arrows of time that we experience seem to emerge. There is the psychological arrow of time, the fact that we remember the past but not the future. This is a direct consequence of entropy. The very act of forming a memory in your brain is an entropy-increasing process. It requires energy. It creates new complex neural connections. It leaves a physical trace. It is a process that moves from a simpler state, no memory, to a more complex and disordered one, a memory. We cannot remember the future, because the irreversible entropy-increasing process of forming that memory has not yet occurred. There is also the cosmological arrow of time, the expansion of the universe itself. The fact that the universe is growing larger, cooler, and more diffuse is in itself a movement towards a more disordered state. The energy of the Big Bang, once concentrated in a single incredibly ordered point, has been spreading out and dissipating for 13.8 billion years, a perfect and colossal example of entropy in action. But this brings us to the deepest and most profound mystery of all. If the second law of thermodynamics dictates that the universe is always moving towards a state of greater disorder, then it must have a logical and inescapable consequence. The universe must have begun in a state of almost perfect and almost unimaginably improbable order. To give time its arrow, the universe had to have a beginning that was a state of incredibly low entropy. The very early universe, just after the Big Bang, must have been the ultimate uncracked egg, the perfectly ordered sandcastle, the perfectly stacked deck of cosmic cards. And this is precisely what our observations of the cosmic microwave background seem to show, a universe that was remarkably smooth, simple, and uniform. Why? Why did our universe begin in this highly specific, incredibly ordered, and statistically miraculous state? This is now one of the biggest unsolved questions in all of physics. We have no definitive answer. Some physicists believe it may have to do with the specific conditions of cosmic inflation. Others wonder if our Big Bang was just one event in a much larger cyclical multiverse, where states of low entropy can occasionally emerge from the chaos by pure chance, over even vaster timescales. But whatever the reason, it is this one foundational fact. The fact that the universe was wound up at the beginning, that gives time its direction. The arrow of time is the story of that great cosmic clock, slowly, inexorably, and beautifully unwinding. As you drift now deeper into the quiet of the night, think of this gentle, universal, and unstoppable flow. See the ink spreading in the water. See the steam rising from a warm cup of tea and dissipating into the cool air. See the stars themselves slowly burning their fuel, radiating their ordered energy out into the disordered darkness of space. These are not just random events. They are all small, quiet manifestations of the great arrow of time. They are the sound of the universe breathing out. And we in our brief and precious lives are privileged to be a part of that one great irreversible exhalation. The arrow of time, the great one-way street of our existence, is a consequence of a single profound fact, that our universe began in a state of almost perfect order. This points our journey inevitably to that ultimate origin point, to the moment that the cosmic clock was wound and the river of time began to flow. But did time truly have a beginning? Can we speak of a moment before which there was no time at all? To explore this, we must now travel to the very edge of existence itself, to the instant of the Big Bang, and ask the most difficult and mind-bending question of all. What came before the beginning? When we hear the phrase the Big Bang, our minds often conjure a powerful and dramatic image. We picture a single tiny brilliant point of light, hanging in a vast pre-existing black void, which then suddenly and violently explodes, like a cosmic firework, flinging out all the stars and all the galaxies into the waiting emptiness. It is a simple, powerful, and intuitive image, and it is, for the most part, completely wrong. To truly approach the great mystery of the beginning, we must first gently and completely let go of this mental picture. The Big Bang was not an explosion in space. It was the beginning of the expansion of space itself. There was no empty void for it to explode into, because there was no outside in the very first moment. The entire universe, all of space, all of time, all of matter and energy, was compressed into a state of almost infinite density and almost infinite temperature. This state, which physicists call a singularity, did not exist at a point in space. It was the entire space. The Big Bang then happened everywhere at once. The very spot where you are resting now, the space occupied by the Earth, the Sun, and the farthest galaxy we can see, all of it, and all the space in between was once part of that single, initial, infinitely dense state. This singularity is a point where our current understanding of physics, our beautiful and powerful theories of general relativity and quantum mechanics, simply break down. They give us nonsensical answers, infinities that tell us our maps of reality are no longer valid. The singularity is a wall, a boundary not of the universe, but of our own knowledge, and it is at this wall that our question, what came before the beginning, becomes so profound, so challenging, and so strange. The most straightforward and perhaps most mind-bending answer from the perspective of classical general relativity is that the question itself may be meaningless. The very concept of before requires the existence of time. Before is a temporal word. It implies a moment that precedes another moment on a timeline. But what if time itself did not exist before the Big Bang? What if time, like space, was created in that first singular moment? This is the incredible idea that has been famously championed by physicists like Stephen Hawking. He used a simple and beautiful analogy to illustrate this profound concept. Asking what came before the Big Bang, he suggested, is like standing at the North Pole and asking what is north of here. The question sounds like a valid one, but it is based on a false premise. Once you are standing at the exact point of the North Pole, the very concept of north ceases to have any meaning. You cannot go any further north. Every direction you could possibly point is by definition south. In the same way, if the Big Bang was the starting point of time itself, the 0 point on the cosmic clock, then there was no before in which anything could have happened. The river of time begins at that source, and the question of what lies upstream of the source itself dissolves into a beautiful logical paradox. This is not a new idea, born from the strange world of modern physics. It has deep and ancient roots in philosophy and theology. More than 1600 years ago, the great Christian theologian and philosopher, Saint Augustine of Hippo, was wrestling with a very similar question. He was often asked by skeptics, what was your God doing for all that eternity before he decided to create the world? It was a clever question, designed to make the idea of a singular moment of creation seem arbitrary and nonsensical. And Augustine, after much thought, arrived at a conclusion of profound genius that predates Einstein by 15 centuries. He wrote that God did not create the world in time, he created the world with time. For Augustine, time was a property of the created universe, not something that existed independently of it. Before the creation there was no before, there was only the eternal timeless now of God. It is a theological idea that has a startling and beautiful resonance with the conclusions of modern cosmology. And yet the human mind is a restless and curious thing. We are storytellers, and we crave a beginning to our stories. And so, while the idea of a beginningless time is the simplest and perhaps most elegant solution, physicists have not been able to resist the urge to peek behind the curtain of the singularity, to imagine, with the tools of theoretical physics, what might have made the Big Bang bang. And these speculative theories, while unproven, are among the most wondrous and beautiful ideas in all of science. One such idea is that of a cyclical universe. In this model, our universe is not a one-time event, but just one chapter in an eternal cyclical story of expansion and contraction. This is the theory of the Big Bounce. It suggests that our Big Bang was the result of the collapse of a previous universe. That universe would have expanded, just like ours, but would have eventually recollapsed under its own gravity in a big crunch, until all of its matter and energy were compressed back down into a new, super-dense singular state, which then bounced, triggering a new Big Bang and the birth of a new universe. In this breathtaking vision, time has no beginning and no end. It is an eternal cycle of death and rebirth, of universes being born from the ashes of their parents, a great cosmic phoenix, forever rising and falling. Another possibility connects us back to the great speculative idea of the multiverse. Perhaps our Big Bang was not a bounce, but a budding. As we explored, the theory of eternal inflation suggests that our universe is just one bubble that formed in a much larger, eternally expanding high-energy vacuum. In this view, our time had a definite beginning, the moment our bubble universe nucleated and branched off from the parent vacuum. But that parent vacuum, the great inflating ocean of space-time, may itself be eternal, timeless, or operating under a different set of temporal rules altogether. Our time began, but it was born from a reality that may have always existed. And then there is the most mathematically abstract, and perhaps most beautiful idea of all, the Hartle-Hawking no-boundary proposal. This idea, born from the strange world of quantum mechanics, suggests that if you could travel back in time to the very beginning, time itself would smoothly and gradually transform into a dimension of space. Let us return to our analogy of the North Pole one last time. As you travel north on the surface of the Earth, the lines of longitude which define east and west all converge. At the exact point of the North Pole, the concepts of east and west vanish. There is only one direction, south. In a similar way, the no-boundary proposal suggests that at the very beginning of the universe, the dimension of time, the direction of before and after, smoothly transformed and became indistinguishable from the dimensions of space. The universe at its origin had 4 spatial dimensions and no time dimension. It is a universe that is finite in the past, but has no beginning edge, no singular point where time starts. It just is. These are all ideas that live on the very farthest shores of our scientific understanding. We do not yet know which, if any of them, is true. The Big Bang remains the great dark curtain at the beginning of our cosmic play. What we know with a great deal of certainty is that our universe of space and time, the great expanding cosmos we inhabit, did indeed begin its current phase in a state of incredible heat and density 13.8 billion years ago, and the arrow of time, the great one-way river of entropy, began its long and patient flow from that moment. As you drift now into a deeper and more peaceful state of rest, let your mind float in this profound mystery. Let go of the need for a simple beginning. Imagine the universe not as a story with a first page, but perhaps as a sphere with no starting point, or as a single beautiful wave in an eternal ocean. The beginning of our time is a place where our physics breaks down, but where our sense of wonder can truly begin. It is the ultimate origin story, a moment so profound that it lies at the very intersection of science, of philosophy, and of the sacred. The Big Bang represents the mystery of time's beginning, a point of infinite density from which our entire cosmic story unfolded. But if time had a beginning, does it also have an end? Our journey into the far future showed us the slow fading of the cosmos in a big freeze, but our own universe contains places where time behaves even more strangely, places where the flow of time seems to stop altogether, where the fabric of reality is torn. To continue our exploration of time's great boundaries, we must now journey to the most extreme and enigmatic objects in the cosmos, to the gravitational prisons from which not even light can escape. We must travel to the edge of a black hole and ask what happens to time when it falls in. To understand a black hole, we must first understand its birth, and its birth is one of the most violent, most spectacular, and most definitive events in the entire universe. Our journey begins with a star, Not a star like our own gentle yellow sun, but a true giant, a supergiant star, many, many times more massive, burning with a brilliant, furious blue-white light. For millions of years this star has lived a grand and tempestuous life, a colossal nuclear furnace hanging in the darkness of space. In its core it has been fusing lighter elements into heavier ones, forging the very atoms that make up our world, and in doing so creating the immense outward pressure of light and heat that holds its own colossal gravity at bay in a perfect, delicate and long-lived balance. But this balance cannot last forever. Inevitably, the star begins to run out of fuel. The nuclear fire in its core, which has raged for millions of years, begins to sputter and die, and in that moment the great balancing act that has defined its entire life comes to a sudden and catastrophic end. The outward push of the fusion furnace is no longer strong enough to resist the relentless, unforgiving, inward crush of its own immense gravity, and the star begins to collapse. The core of the star implodes with a speed and a violence that is almost instantaneous. In less than a second, a core the size of our own Earth is crushed down to a ball just a few miles across, the sphere of almost perfectly dense neutron matter. This catastrophic collapse triggers a rebound, a shockwave that rips back out through the star's outer layers, blowing the vast majority of the star's material out into space in a single titanic explosion. This is a supernova. For a few brief weeks, this single dying star can outshine an entire galaxy of billions of stars, becoming the brightest object in the heavens. It is one of the most brilliant and energetic events in the cosmos. But our story is not with the explosion, it is with what is left behind. If the remnant of the collapsed core is massive enough, roughly more than 3 times the mass of our own sun, then nothing in the universe can stop its final collapse. No known physical force, not even the immense pressure of the neutrons themselves, can resist the final, absolute and terrifying victory of gravity. The core continues to collapse, and collapse, and collapse, until all of its immense mass is crushed down into an infinitely small, infinitely dense point, a singularity. At this point, the gravity is so intense that it warps the very fabric of space-time around it into a closed, inescapable curve. It creates a gravitational well so deep that nothing, not even light itself, the fastest thing in the universe, can escape its pull. A black hole is born. It is a tear in the fabric of reality. It is a one-way door in the universe. It is a place where the laws of physics as we know them break down. And it is a place where time as we know it behaves in the most bizarre and unimaginable ways. Let us now take a slow, imaginary journey towards one of these strange and silent objects. Let us imagine an intrepid astronaut. We will call her Ilara, who is on a mission to explore a black hole from a safe distance, while we, as her mission control, watch her on our screens from our own, even safer, spaceship, very far away. As Ilara's ship gets closer to the black hole, the first strange effects of its immense gravity begin to appear. We, from our distant vantage point, would begin to see the effects of extreme gravitational time dilation. The powerful gravity of the black hole is stretching the fabric of space-time, and so it is stretching time itself. We would notice that the clock on her ship is beginning to tick more slowly than our own. At first the difference is infinitesimal, a matter of microseconds, but as she gets closer and closer to the black hole, the effect becomes more and more pronounced. We would see her moving in what appears to be a graceful and deliberate slow motion. If she were to wave to us, her wave would seem to take an impossibly long time to complete. Her time is slowing down relative to ours. We would also see the effect of gravitational redshift, the light from her ship, as it struggles to climb out of the black hole's immense gravity, loses energy, and as light loses energy, its wavelength is stretched, shifting it towards the red end of the spectrum. We would see the image of her ship become redder and dimmer and fainter as it gets closer to the edge. Now let us imagine that in an act of ultimate scientific curiosity, Ilara decides to cross the point of no return. This boundary, this invisible spherical surface from which escape is impossible, is called the event horizon. As Alara falls towards this invisible line, something truly strange and profound would happen from our perspective. Her clock would seem to tick slower and slower and slower, until as she reached the exact point of the event horizon, her time from our point of view would seem to stop completely. Her movements would freeze. Her image would become infinitely redshifted, fading from red to infrared to radio waves and then to nothing. We would see a final frozen ghostly image of her, held forever in time at the very edge of the abyss. We would never ever see her cross. But what about Alara? What is her experience? For her, as she falls towards the black hole, nothing seems out of the ordinary at first. Her own clock is ticking perfectly normally, 1 second per second. She feels no strange forces. If she is falling towards a very large supermassive black hole, she could cross the event horizon without even noticing. For her, there is no wall, no barrier, no dramatic moment. She would simply float in a state of perfect freefall across an invisible and mathematically defined line in space. But as she crosses that line, the universe she has left behind would appear to do something spectacular. As she looks back, the extreme curvature of space-time would bend the light from the distant cosmos, allowing her to see the entire future history of our universe play out in a brilliant, fast-forwarded display. She would see the stars of our galaxy age and die in an instant. She would see the galaxies themselves evolve and merge. She would see the entire trillion-year future of the cosmos flash before her eyes in the few moments it takes her to continue her journey. And once she is inside the event horizon, her fate is sealed. The rules of space-time have now fundamentally changed. Outside the black hole, you can move in any direction you like in space, forwards, backwards, left, right, but you are forced to move in only one direction in time, forward into the future. Inside the black hole, this is reversed. The dimension of space pointing towards the singularity at the center now becomes time-like, and the dimension of time becomes space-like. What this means is that to move towards the singularity is now as inevitable as it is for us to move towards tomorrow. You cannot stop. You cannot turn back. You cannot even stand still. Every possible future path you could take, every direction you could point your ship, now ends at the singularity. The singularity is not a place in space anymore. It is a moment in time. It is the final moment, the end of your own personal timeline. And as you approach that final moment, if it were a smaller stellar mass black hole, the tidal forces would become immense. The gravity at your feet would be so much stronger than the gravity at your head that you would be stretched, elongated, and pulled apart in a process that physicists have given the wonderfully graphic name spaghettification. You would be torn into a thin stream of your constituent atoms, all flowing inexorably towards the center. And at the center is the singularity itself, a point where the curvature of space-time becomes infinite, a point where the density of matter becomes infinite. It is a point where all of our known laws of physics, including Einstein's own theory of relativity, break down completely. We do not know what happens at the singularity. It is a place where science ends, and we are left only with speculation. It is in a very real sense the end of time itself. As you drift now into the deep and quiet stillness of sleep, let this strange and beautiful paradox settle in your mind. The black hole is a place where time from the outside seems to freeze forever at its edge, and where time on the inside rushes inexorably towards a final, absolute, and singular end. It is a one-way door in the fabric of the universe, a place where the river of time flows in but never flows out. It is a monument to the ultimate and absolute victory of gravity over all other forces. It is the quiet, dark, and perfect silence at the very end of the story. The black hole represents time's final, absolute end, a point of infinite density where the river of moments simply ceases to flow. It is the ultimate mystery on the largest of scales. But what if time has another equally strange boundary, not at its end, but at its very beginning, in its smallest possible increment? Is time a smooth, continuous, flowing river, or is it more like the frames of a movie, a series of tiny, discrete, indivisible moments, ticking by at the most fundamental level of reality? To continue our journey, we must now leave the crushing gravity of the black hole and travel to the opposite end of the scale, to explore the strange, pixelated world of Planck time. For our entire lives and for all of human history, we have experienced time as a smooth and unbroken current. It is a river, flowing effortlessly and seamlessly from one moment to the next, carrying us from a past we can only remember, through a present we can only briefly touch, and into a future we can only imagine. We do not feel any gaps in this flow. We do not feel any stutters or any seams in the great invisible fabric of moments. Our consciousness experiences a world that is continuous, that is analog, and that is perfectly, beautifully fluid. This smooth and unbroken flow is the most fundamental experience of our reality. But what if this smoothness is an illusion? A beautiful and convincing illusion, but an illusion nonetheless? What if it is a trick of scale, an artifact created by the limitations of our own perception? What if time at its most fundamental, most microscopic level is not a smooth flowing river at all? What if instead it is a series of tiny, discrete and indivisible ticks, like the individual frames of a cosmic film, clicking by at a speed so unfathomably fast that they create the perfect and complete illusion of continuous motion? To understand this radical and mind-bending idea, let us think for a moment about a modern movie projected onto a large screen. As you watch, you see a world of fluid, continuous movement. A person walks across the screen, a car drives by, a leaf falls gracefully from a tree, but what you are actually seeing is a rapid succession of completely still, frozen images. 24 individual, static frames flashed before your eyes every single second. Your brain, unable to process these images as separate events, blurs them together, creating the seamless illusion of motion. The motion is not fundamentally real. It is a perception created by the rapid succession of still moments. Now, let us ask a profound question. What if the universe itself operates on the same principle? What if reality is not an analog river but a digital stream? This is one of the most incredible and deeply strange ideas to emerge from the world of quantum physics, and it begins with a man who in the year 1900 reluctantly opened the door to this new reality. His name was Max Planck. The German physicist Max Planck was studying a deep puzzle related to the energy emitted by hot objects. The prevailing theories of his time, which treated energy as a continuous wave-like phenomenon, simply could not explain the experimental data. In an act of what he later called desperation, he proposed a radical new idea. He suggested that energy was not continuous. He proposed that it could only be emitted or absorbed in tiny, discrete packets or bundles. He called these indivisible packets of energy quanta. This was the birth of quantum mechanics, and it was the first great hint that the universe, at its deepest and most fundamental level, might be granular or pixelated, rather than smooth and continuous. From this revolutionary idea, Planck and the physicists who followed him, including Einstein, realized that by combining the three most fundamental constants of nature, the speed of light, the gravitational constant, and Planck's own constant of quantum action, one could derive a set of natural units. These are not arbitrary units, like the foot or the second, which are based on human conventions. These are the universe's own inherent and fundamental units of measurement for length, mass, and time itself. They are, in a sense, the universe's own building blocks. And the smallest possible meaningful unit of time that emerges from these equations is now known as Planck time. Planck time is a duration so infinitesimally, so absurdly short, that our minds can barely begin to comprehend it. It is defined as the time it would take a photon, a particle of light, traveling at the ultimate cosmic speed limit, to cross a distance equal to the Planck length, which is the smallest possible meaningful unit of distance. Any duration shorter than 1 unit of Planck time is, according to our current understanding of physics, physically meaningless. It is the single indivisible frame in the movie of reality. Let us try to grasp the scale of this. 1 unit of Planck time is approximately 10 to the power of minus 43 seconds. That is a decimal point, followed by 42 zeros and then a 1. To say that this is a small number is a profound understatement. Let us try an analogy. There are more units of Planck time in a single simple second than there are seconds in the entire 13.8 billion year history of the universe. From the moment of the Big Bang to this very moment as you lie here listening to these words. Let that immense, almost terrifying scale settle in your mind. The universe's frame rate, the number of individual frozen moments that make up each second of our perceived reality, is a number so vast it transcends our ability to imagine. If time is indeed quantized, if it is made up of these discrete ticking moments, then it has profound and deeply strange implications for the nature of our reality. It means that there is no such thing as an instant. The smooth flowing now that we feel is an illusion. There is only the duration of one Planck time, and then the next and then the next. Change itself, at its most fundamental level, does not happen smoothly. It happens in a series of tiny, almost imperceptible, quantum jumps. The universe is not a river. It is a stroboscope flashing with a speed that creates the perfect illusion of a continuous flow. It also means that there is a fundamental limit to our knowledge of the universe. Below the scale of the Planck time and the Planck length, our current laws of physics, including Einstein's beautiful theory of general relativity, with its smooth geometric fabric of space-time, simply break down. This is the realm where the quantum foam that we have spoken of before is thought to exist, a chaotic probabilistic world where space and time are no longer coherent concepts. The smooth river of time, when you zoom in far enough, dissolves into a chaotic, unknowable mist. This idea of a pixelated space-time also offers a beautiful and elegant solution to a series of philosophical paradoxes that have haunted thinkers for thousands of years. The ancient Greek philosopher Zeno of Elea famously argued that motion itself should be impossible. In his most famous paradox, the great hero Achilles is in a race with a tortoise. The tortoise is given a head start. Zeno argued that for Achilles to catch the tortoise, he must first reach the point where the tortoise started, but by the time he gets there, the tortoise has moved a little further ahead. Now Achilles must reach that new point, but by the time he gets there, the tortoise has moved on again just a little. This continues on and on in an infinite series of smaller and smaller steps, and so Zeno concluded, with a logic that is difficult to argue with, that Achilles can never ever catch the tortoise. This paradox arises from a single hidden assumption that space and time are infinitely divisible. But if our universe is quantized, if there is a smallest possible unit of distance, the Planck length, and a smallest possible unit of time, the Planck time, then the series of steps is not infinite. There is a final, smallest step, and in the very next tick of Planck time, Achilles does in fact overtake the tortoise. The strange quantum nature of reality comes to the rescue of our common sense. As you drift now deeper into the quiet of the night, think of this dual nature of time. The time we feel, the time of our lives, is a smooth, flowing, analog river. But the time of the universe at its deepest and most hidden level may be a staccato, ticking, digital clock, moving forward in a series of impossibly tiny, discrete and perfect steps. The idea that time may be a series of discrete, frozen moments, like the frames of a cosmic film, challenges our deepest intuitions. It makes the flow of time an illusion, a trick of perception created by our minds stringing these frames together. But this leads to an even more profound and unsettling idea, one that comes not from the quantum world but from the strange geometric reality of Einstein's space-time. What if all the frames, the past, the present and the future, are not just fleeting moments but already exist simultaneously and forever? What if the river of time is not a river at all, but a solid frozen block of ice, and our consciousness is merely a dim light shining on one sliver of it? To continue our journey, we must now explore the most bizarre and deterministic of all temporal concepts, the theory of the block universe. For our entire lives, we have been taught to think of time in a very specific way. We see it as a line upon which we are traveling. The past is the part of the line that is behind us, fixed, unchangeable, and gone forever. The future is the part of the line that is ahead of us, open, unwritten, and not yet real. And the present, the now, is that one special, magical, and fleeting point where the future becomes the past. This is the moving spotlight of our consciousness. This idea, known as presentism, feels deeply and intuitively true. It is the very foundation of how we experience our lives. But what if this intuition, as powerful as it is completely wrong? What if the past is not gone? What if the future is not unwritten? What if the past, the present, and the future are all equally real, all coexisting in a single vast and timeless structure? This is the central idea of a theory known as eternalism, and its physical manifestation is the concept of the block universe. To understand this, let us use a simple and gentle analogy. Imagine a loaf of bread. The entire loaf, from its first slice to its last, represents the entire history of the universe, the four-dimensional block of space-time. Each individual slice of the loaf is a single now. It is a complete three-dimensional snapshot of the entire universe at one particular moment in time. The very first slice of the loaf is the Big Bang. The very last slice is the final cold state of the Big Freeze, and every single moment in between. The formation of the first stars, the birth of our own sun, the age of the dinosaurs, the moment of your own birth, this very moment right now as you listen to these words, and every moment that you will ever live in your future, is just another slice, already existing, silent and complete within the loaf. In this view, the flow of time that we experience is an illusion. Our consciousness is like a small spotlight, slowly moving along the loaf, illuminating one slice at a time. The slice that is currently under the spotlight is what we call the present. The slices the spotlight has just passed over are what we call the past, and the slices that are still in the dark further down the loaf are what we call the future. But just because our light is only shining on one slice, it does not mean that the other slices do not exist. The entire loaf is already there. The past, the present, and the future are all equally real, all existing simultaneously as part of this great four-dimensional block of space-time. This is a profoundly strange and unsettling idea, but it is not just a philosophical fancy. It is a conclusion that arises directly from the strange reality of Einstein's theory of relativity. As we explored in our previous chapter, Einstein showed us that time is not absolute. The rate at which time passes depends on your motion. This leads to a strange phenomenon known as the relativity of simultaneity. What this means is that two different observers, moving at different speeds, will have a different definition of what is happening now across the universe. Let us imagine a thought experiment. You are standing on Earth, and far away on a spaceship traveling past at a very high speed is your friend. At the exact midpoint between the two of you, a star explodes in a supernova. From your perspective, the light from that supernova reaches both you and your friend at the exact same time. The two events, the light reaching you and the light reaching your friend, are for you simultaneous. They happen in the same now. But for your friend who is moving, the situation is different, because they are traveling towards the light that is coming from in front of them, and away from the light that is coming from behind. They will see the light from the supernova at a different moment than you do. Their definition of a single slice of now across the universe will be tilted. Relative to yours, what you consider to be the present might for them be a mixture of your past and your future. The profound implication of this is that if there is no single universal objective now that everyone in the universe can agree on, then the idea of the present being a special, uniquely real moment collapses. If my now can be in your past and your now can be in my future, then all moments, past, present, and future, must be equally real. They must all coexist. The universe cannot be a single flowing river. It must be a solid pre-existing block. This idea, if it is true, has two beautiful and deeply comforting implications. The first is that the past is not gone. It has not vanished into a non-existent void of memory. Every moment you have ever lived, your first steps, the sound of a loved one's laughter, a quiet moment of perfect peace watching a sunset, is not just a fading echo in your mind. It is a real, existing and permanent part of the structure of space-time. It is a slice in the great cosmic loaf, just as real and just as valid as the slice you are experiencing right now. Those moments are not lost to you. You are simply no longer in that location in time. In a very real sense, the block universe grants a kind of immortality to every moment of our lives. They are not fleeting. They are eternal. The second and more challenging implication concerns the future. If the future already exists, if it is just another part of the block that we have not yet reached, then what does this say about our own free will? Are our choices real? Or are we simply playing out a pre-written script? Our lives nothing more than a movie that is already finished, and we are just watching it, frame by frame. This is one of the deepest philosophical paradoxes that the block universe presents. And there is no easy answer, but one way to think about it is that our choices and our feeling of free will are not an illusion. They are the very mechanism by which the future is what it is. Your life is a unique and specific path, traced through the four-dimensional block of space-time. The feeling of making a choice is your subjective experience of following that path. The path may already exist, but you are the one who is walking it. Perhaps free will and a determined universe are not enemies, but two different ways of describing the same beautiful and deeply complex reality. As you drift now deeper into the quiet of the night, let this immense and calming idea settle in your mind. Let go of the anxious feeling of time slipping away. Let go of the idea of a past that is lost and a future that is uncertain. Instead, imagine your life as a long, beautiful and indelible thread woven into the eternal fabric of all of existence. The block universe transforms time from a fleeting, unstoppable rush into a vast, serene and timeless landscape. It suggests that our lives are not a brief flicker in the darkness, but a permanent and meaningful part of the great, silent and unchanging structure of reality. The block universe, born from the physics of the very large, paints a picture of a static, eternal reality where all of time exists at once. But what happens when we journey to the other end of the scale, to the strange and probabilistic world of the very small? Here in the realm of quantum mechanics, time becomes even more bizarre. It is a world where particles can be linked across time, where the future can seem to influence the past, and where in the universe's most fundamental equations, time itself seems to vanish altogether. To continue our journey, we must now leave the frozen river of space-time and enter the shimmering, uncertain fog of the quantum clock. For all its mind-bending strangeness, Einstein's relativity gives time a central and dramatic role in the cosmos. Time is a character. It is a dimension, a fabric that can be bent, stretched, and warped by gravity and motion. It is a physical, dynamic entity. But as we leave this grand cosmic scale and descend into the world of the very, very small, into the flickering, probabilistic realm of quantum mechanics, time begins to behave in a very different and even more mysterious way. Here, in the world that governs atoms, electrons, and photons, time seems to lose its starring role. It becomes a ghost in the machine. Let us start with the foundational equation of modern quantum physics, the great Schrödinger equation. In its simplest form, it is a beautiful and powerful recipe that describes how a quantum system, the wave function, or the cloud of probabilities of a single particle, evolves from one moment to the next. But there is something deeply strange about the role that time plays in this equation. Unlike in relativity, where time is flexible and interwoven with space, the T for time in Schrödinger's equation is a rigid, external and absolute parameter. It is a universal background clock, a silent metronome that ticks at the same steady rate for everything in the quantum world. It is, in essence, Newton's absolute time, resurrected from the dead and placed at the very heart of our most modern theory of reality. This creates a profound and deeply unsettling schism in the heart of physics. Our best theory of the very large general relativity tells us that time is relative, flexible, and dynamic, and our best theory of the very small quantum mechanics seems to require that time is absolute, rigid, and universal. These two great pillars of modern science are built on fundamentally contradictory concepts of time, and this conflict comes to a head when physicists try to do the one thing they want to do more than anything else: unite the two theories into a single beautiful theory of everything, a theory of quantum gravity. When they attempt to do this, when they try to write down an equation that describes the quantum state of the entire universe, a bizarre and shocking thing happens. In one of the most famous and perplexing equations in all of theoretical physics, the Wheeler-DeWitt equation, the variable for time simply drops out. It vanishes completely. The equation that is meant to describe the entire universe, at its most fundamental level, is timeless. It describes a static, frozen, and unchanging quantum now, a universe where in a sense nothing ever happens. This is what physicists call the problem of time. Our two best descriptions of reality give us completely contradictory pictures of what time is, and when we try to merge them, time disappears altogether. This has led many physicists and philosophers to a radical and profound idea that time as we experience it may not be a fundamental ingredient of the universe at all. Instead, it may be an emergent phenomenon. To understand what this means, let us use an analogy. Think of temperature. If you could look at a single individual molecule of water, it would be meaningless to ask what its temperature is. A single molecule does not have a temperature. Temperature is a property that only emerges when you have a vast collection of trillions of molecules. It is a macroscopic property, an average of the collective motion of all those molecules. It is real to us. We can feel it, we can measure it, but it is not a fundamental property of any single one of its constituent parts. Perhaps time is like this. Perhaps at the most basic, fundamental quantum level of reality, time does not exist. There is only a static, timeless state, and our powerful, intuitive experience of a flowing directional time is an emergent phenomenon, something that only appears when you zoom out to our larger, more complex classical world. It is a property that emerges from the intricate relationships and interactions of a countless number of quantum events. It is, in a sense, a trick of statistics, a macroscopic illusion born from a timeless microscopic reality. The strange world of quantum mechanics offers other clues that time is not what it seems. Consider the phenomenon of quantum entanglement, which Einstein famously called spooky action at a distance. It is possible to link two particles together in such a way that they share a single unified quantum state. If you then separate these two particles, even by a distance of billions of light years, they remain connected. If you measure a property of one particle, you will instantly know the corresponding property of the other. The information seems to travel between them instantaneously, far faster than the speed of light, in a way that seems to violate our classical notions of space and time. Some physicists have even speculated that the arrow of time itself might be a consequence of this growing entanglement. The idea is that, as the particles in the universe interact with each other, they become more and more entangled, creating a more and more complex web of connections. And it is this ever-increasing complexity, this growth of quantum entanglement, that we perceive as the forward flow of time, and the quantum world offers up an even more bizarre and unsettling challenge to our understanding of time and causality. It is a famous thought experiment first proposed by the physicist John Wheeler, called the delayed choice experiment. In a normal quantum experiment, a particle can behave either as a solid particle or as a spread-out wave, depending on how you choose to measure it. If you measure which path it takes, it behaves like a particle. If you don't, it behaves like a wave. But in the delayed choice version, you wait to decide whether or not to measure the path until after the particle has already passed the point where it would have had to choose whether to be a wave or a particle. The bizarre and experimentally confirmed result is that the particle seems to know in the past what choice you are going to make in the future. The measurement you make in the present seems to reach back in time and change the history of the particle. This is not time travel. It is a phenomenon that physicists call retrocausality, and it suggests that at the quantum level, the neat, linear one-way street of cause and effect that we experience in our daily lives may be a much more complex and perhaps even two-way affair. The future can, in a strange and subtle way, seem to influence the past. As you drift now into a deeper and more peaceful state of rest, let your mind float in this shimmering, uncertain, and deeply mysterious quantum fog. It is a world where our most basic intuitions about time, that it is continuous, that it is absolute, that it only flows forward, all seem to dissolve. It is a world where time can be a rigid external background in one equation, and can vanish completely in another. A world where the future can seem to reach back and touch the past. It suggests that our firmest and most intuitive sense, the feeling that time is a great flowing river, may be the most beautiful and most profound illusion of all. This raises a profound question. If the flow of time is not a fundamental law of the universe, then where does our powerful shared experience of it come from? The answer, it seems, may lie not in the stars or in the atoms, but in ourselves, in the ancient biological clocks that tick silently within every cell of our bodies. To continue our journey, we must now turn away from the strange equations of physics and enter the quiet, rhythmic, and deeply familiar world of the circadian rhythm. This is one of the deepest philosophical paradoxes that the block universe presents, and there is no easy answer, but one way to think about it is that our choices and our feeling of free will are not an illusion. They are the very mechanism by which the future is what it is. Your life is a unique and specific path, traced through the four-dimensional block of space-time. The feeling of making a choice is your subjective experience of following that path. The path may already exist, but you are the one who is walking it. Perhaps free will and a determined universe are not enemies, but two different ways of describing the same beautiful and deeply complex reality. As you drift now deeper into the quiet of the night, let this immense and calming idea settle in your mind. Let go of the anxious feeling of time slipping away. Let go of the idea of a past that is lost and a future that is uncertain. Instead, imagine your life as a long, beautiful, and indelible thread woven into the eternal fabric of all of existence. The block universe transforms time from a fleeting, unstoppable rush into a vast, serene, and timeless landscape. It suggests that our lives are not a brief flicker in the darkness, but a permanent and meaningful part of the great, silent, and unchanging structure of reality. The block universe, born from the physics of the very large, paints a picture of a static, eternal reality where all of time exists at once. But what happens when we journey to the other end of the scale, to the strange and probabilistic world of the very small? Here, in the realm of quantum mechanics, time becomes even more bizarre. It is a world where particles can be linked across time, where the future can seem to influence the past, and where, in the universe's most fundamental equations, time itself seems to vanish altogether. To continue our journey, we must now leave the frozen river of space-time and enter the shimmering, uncertain fog of the quantum clock. For our entire journey, we have been looking outwards. We have gazed at the vast, expanding universe, at the warping fabric of space-time, at the distant, dying light of the Big Bang. We have looked for the nature of time in the heavens, and in the strange, timeless equations of the quantum world. But what if the most intimate and important clock of all is not out there but in here? What if the most profound story of time is the one being told, at this very moment, in the silent, rhythmic pulse of your own body? Long before our ancestors ever carved a mark on a sundial, long before the first clock was ever built, life on Earth had already learned to tell time. It learned to listen to the great fundamental rhythm of our own planet, the slow, steady 24-hour cycle of light and darkness. And in response to this rhythm, life developed its own internal clock. This is the circadian rhythm from the Latin circa diem, meaning about a day. It is not just a sleep-wake cycle. It is a deep, ancient and incredibly complex biological orchestra that governs nearly every process in our bodies, from our hormone levels to our body temperature, to our metabolism and our mood. At the center of this orchestra there is a single master conductor. It is a tiny pinhead-sized cluster of about 20,000 neurons located deep within the hypothalamus of your brain. It is called the suprachiasmatic nucleus, or SCN, and its location is a marvel of biological engineering. It sits directly above the point where the optic nerves from your eyes cross on their way to the back of the brain. This strategic location allows the SCN to receive direct information about the most important time cue in our world, night. Let us imagine the process as it is happening for you now and as it will happen tomorrow. As the first faint rays of morning sunlight enter your eyes, a signal travels down your optic nerve directly to this master clock. The SCN then sends out a cascade of chemical and electrical signals to the rest of your body, a message that says, "The day has begun. It is time to wake. It is time to be active." It is your body's way of synchronizing its own internal time with the great external clock of the rising sun. It is a daily, gentle and absolutely vital reset. But the SCN is not the only clock in your body. It is just the conductor. The orchestra itself is vast. We now know that nearly every organ and perhaps every single cell in your body has its own smaller peripheral clock. Your liver has a clock. Your stomach has a clock. Your muscles have a clock, and it is the job of the master conductor in your brain to make sure that all of these countless individual clocks are playing in harmony. One of the most important instruments in this orchestra is the pineal gland, which the SCN directly controls. As the light of day fades into the evening, the SCN sends a signal to the pineal gland to begin producing a hormone called melatonin. Often called the hormone of darkness, melatonin is not a sleep aid in the way a sleeping pill is. It is a sleep facilitator. Its rising levels in your bloodstream do not knock you out. They simply and gently quiet the daytime signals in your brain, opening the gates for sleep to arrive. This internal clock also governs the slow, steady rhythm of your body temperature, which naturally drops to its lowest point in the early hours of the morning, helping to promote deep sleep, and then begins to rise again just before you wake up. It controls your metabolism, making your digestive system more active and efficient during the day. It even controls your immune system, which becomes more active at night, and the great silent work of cellular repair, which happens most profoundly while you are in a state of deep, restorative sleep. Sleep is not just a period of inactivity. It is the time when your body's own ancient internal clock directs a vast and vital crew of maintenance workers to repair and rebuild you from the inside out. And what is truly fascinating is that this internal clock is not the same for everyone. We each have our own unique and largely genetic chronotype. Some of us are morning larks. These are the people whose internal clocks run a little bit fast. They wake up early, naturally, and often feel their most alert and productive in the morning. Others are night owls, people whose internal clocks run a little bit slower. They struggle to wake up in the morning, but they come alive in the evening, hitting their peak of creativity and alertness just as the rest of the world is winding down. In our modern world, this has created a new and very modern problem: social jet lag. Our society, with its 9-to-5 workday and its early school start times, is a society that is built by and for the morning larks. For the natural night owls, this means they are in a constant state of low-level jet lag, their internal biological time constantly at war with the external social time that is demanded of them. And this ancient biological rhythm is easily disrupted by our modern world. When we travel across time zones, our master clock in the brain might adjust to the new light-dark cycle in a day or two, but the peripheral clocks in our organs can take much longer to catch up, leading to that familiar disorienting feeling of jet lag. and the constant exposure to artificial light in the evening, particularly the blue light from our phones and tablets and computer screens, can trick our master clock into thinking it is still daytime, suppressing the release of melatonin and pushing our natural sleep time later and later into the night. So, after our long and cosmic journey, we arrive at this final, intimate truth. For all the strange and wonderful ways that time can be stretched by gravity or bent by speed or pixelated at the quantum level, the time that matters most to our well-being is this ancient biological rhythm. A rhythm that connects us to the very first life on Earth that learned to tell the difference between day and night. And so we bring our journey to its final, quiet conclusion. We began by asking a simple question: what is time, really? And we have found that there is no single simple answer. Time is a psychological illusion, a trick of memory and attention that stretches and shrinks with our emotions. Time is a human invention, a history of ever more precise clocks designed to bring order to our world. Time is a physical dimension, a part of the fabric of space-time that is relative and flexible. Time is an arrow, an emergent property of the universe's long, slow journey from order to disorder. Time is a mystery at its beginning and a mystery at its end. It is a puzzle in the quantum world, and it is a biological pulse beating silently inside of you. Time, it seems, is a tapestry, woven from all of these threads. It is both an objective feature of the universe and a deeply personal human experience. As our exploration finally comes to an end, let go of all these vast and complex questions. Let go of the need to find a single, definitive answer. Instead, simply feel the gentle, rhythmic, and ancient clock that is ticking within you. It is a rhythm that has been passed down through an unbroken chain of life for billions of years. It is a clock that knows with a deep and profound wisdom exactly what it needs to do. And right now, as the night deepens, as the world outside grows still, this ancient internal clock is gently and quietly preparing you for rest. All you have to do is trust it. All you have to do is let go. The universe doesn't have to end for it to matter. It just has to be, and you are a part of it. A flicker of thought in an ocean of being. And now, you can rest.